section, we're looking at the Earth's spheres, and these two images are great because for the first time they let humanity see Earth differently from ever before. So here in this image, we could see the Apollo 8 astronauts emerge from behind the moon, which you could see here at the bottom part of the image, and in December 1968, and this classic image lets people see Earth differently than ever before. So we could see all the four spheres interacting. We could see the atmosphere with the clouds appearing on this Earth. We could see the lithosphere, the land mass. We could see the hydrosphere and the biosphere with the vegetation. So again, the Earth is made up of four spheres, which I just mentioned, and here's another example of these spheres interacting with one another. The shoreline is one obvious example of an interface, a common boundary where different parts of a system interact. So in this scene, ocean waves, which represent the hydrosphere, were created by the force of moving air, which represents the atmosphere, which here it's breaking against a rocky shoreline, which is known as our lithosphere. So these spheres can be studied separately, however, the parts are not isolated. Each is related in many ways to the others, producing a complex and continuously interacting whole that we call the Earth system. So here for the geosphere, it consists of the solid Earth. It extends from the surface to the center, which is approximately 6,400 kilometers. And the surface of the lithosphere is very uneven. Like we know, it contains high mountainous topography as well as low areas such as Death Valley, portions of which lie below sea level. So it includes the crust, mantle, outer core, and inner core. The atmosphere, which we'll be learning a lot in our course this year, this is the gaseous portion of a planet, the planet's envelope of air. So this thin blanket of air is nevertheless an integral part of the planet. It not only provides the air we breathe, but also acts to protect us from the dangerous radiation emitted by the sun. And we will learn that weather occurs in the lower layer of the atmosphere, which is our first layer known as the troposphere. And 99% of the atmosphere is within 30 kilometers of Earth's surface. Now here in this image of the atmosphere, this was taken from the space shuttle, and we can see the thin streaks here. The thin white wispy streaks are called noctilucent clouds, which are found 80 kilometers high. And we can see that here on the y-axis, the altitude in kilometers. And it is in the dense troposphere that practically all weather phenomenon occur. So here we could see the troposphere layer and the top of the troposphere, which we will learn in the diagram, is the boundary called the tropopause. Okay, so the Earth's surface and the tropopause. Now, again, this is a beautiful image showing us the noctilucent clouds, the thin, wispy clouds that glow with a blue or silvery hue at night when illuminated by sunlight from below the horizon. And noctilucent clouds, they are the highest clouds in our atmosphere, forming in the layer known as the mesosphere, around 80 kilometers, like we saw with the previous image with the altitude on the y-axis. Noctilucent clouds only appear during the summer months and only at latitudes between about 45 and 80 degrees north or south of the equator. But recently, however, in the northern hemisphere, noctilucent clouds have been seen at much lower latitudes than expected. Scientists believe that this could be contributed to climate change, but it could also be due to other factors such as rocket launches expelling particles into the atmosphere, which go on to form noctilucent clouds as well. The hydrosphere, this is the water portion of our planet, and the oceans make up 71% of the Earth's surface. And the hydrosphere includes the water droplets that form clouds, the lakes, rivers, streams, the glaciers, as well as underground water. So the hydrosphere is a dynamic mass that is continually on the move, evaporating from the oceans to the atmosphere and then precipitating to the land and running back to the ocean again, which is known as the hydrologic cycle. And more than 97% of the hydrosphere is found in the oceans and seas, and less than 1% of Earth's water is found in the atmosphere, lakes, streams, and groundwater. And we can see here with this image, nearly 2% of water is frozen. Now, for the Earth's spheres, the biosphere is another component. The biosphere includes all life on Earth. So this ranges from the smallest bacteria or viruses to the largest whale, and we as humans are part of the biosphere as well, and vegetation. Plants and animals depend on the physical environment for the basics of life. However, organisms do more than just respond to their physical environment. Through countless interactions, life forms help maintain and alter their physical environment. Without life, the makeup and nature of the atmosphere, hydrosphere, and lithosphere would be very different. And the ocean contains a significant portion of Earth's biosphere. The modern coral reefs are unique and complex examples and are home to about 25% of all marine species. And again, with climate change, coral reefs are impacted greatly. So we were looking at the spheres. So scientists have recognized they must learn how the Earth's individual components, the land, water, air, and life forms, are interconnected. And for a system, the proper definition, a system is a group of interacting or independent parts that form a complex whole. So, for example, what we just reviewed, the Earth system, including the four spheres. The hydrologic cycle, this is a subsystem of the Earth system, and this is when matter is recycled over and over again. So the water is recycled over and over again in this case. So water readily changes state from liquid to gas to solid at the temperatures and pressures occurring on Earth. And this cycle traces the movements of water among Earth's four spheres. It is one of many subsystems that collectively make up the Earth system, like I just mentioned before. So again, with the hydrologic cycle, we have water evaporating from the oceans, and this is in its gaseous state, the water vapor. And as we will learn later in lecture, as we go higher in altitude, temperature decreases and it cools as we go higher up in the atmosphere. So once it cools, water vapor can condense and form cloud droplets, which is the form of condensation. And then this cloud will travel and eventually it will get heavier with water droplets that it will have to precipitate as rain or snow. And as rain falls on land, it can either be classified as overland flow, so it will run across the land surface, or stream flow, and the water will tunnel into a stream, eventually going into lakes or the oceans. Also, it can infiltrate underground. So that is the process of the hydrologic cycle and water recycling throughout the four spheres. So the composition of the atmosphere. So the air is a mixture of many discrete gases in which varying quantities of tiny solid and liquid particles are suspended. And the composition of air is not constant. It varies from time to time and from place to place. And oxygen and nitrogen make up 99% of the volume. So here on this graph, on this pie chart, we could see nitrogen is the most abundant at 78%, and then followed by oxygen at 20%. Although nitrogen and oxygen are the most plentiful components of the atmosphere and are of great significance to life on Earth, they are of little or no importance in affecting weather phenomenon. Whereas carbon dioxide does affect the weather, as we know, carbon dioxide is a greenhouse gas. So currently, carbon dioxide is at 405 parts per million in our atmosphere, and carbon dioxide is a greenhouse gas, so it absorbs energy. Specifically, it absorbs long wave infrared radiation. And carbon dioxide is part of the carbon cycle. Here we could see a graph. So this is the atmospheric carbon dioxide has been measured at Mauna Loa Observatory in Hawaii since 1958. So there has been a consistent increase since monitoring began. So here on the x-axis, we can see from 1960 to 2020 that carbon dioxide parts per million has increased. Okay, and at this point in 2020, it surpassed 400 parts per million. And much of this rise is attributed to the burning of ever-increasing quantities of fossil fuels such as coal and oil, and some of this additional carbon dioxide is absorbed by the ocean or it is used by plants, but more than 40% remains in the air. Estimates project that by sometime in the second half of the 21st century, atmospheric carbon dioxide will be twice as high as pre-industrial levels. Another greenhouse gas is water vapor, and the amount of water vapor in the air varies considerably from practically none to up to about 4% by volume. And water vapor is important because it is the source of clouds and precipitation. Like I just mentioned before, I described that process of water vapor as it is rising up in the atmosphere. It will cool and condense, forming clouds and then eventually precipitating rain or snow. And aerosols are very small solid and liquid particles. Examples of that would be dust, soot, sea salt, and sea salt. And they may originate from many sources, both natural and human-made, and include sea salt from breaking waves, fine soil blown into the air, smoke and soot from fires, pollen and microorganisms lifted by the wind, and ash and dust from volcanic eruptions, and more. So aerosols can either absorb or reflect radiation depending on the type of aerosol it is. And aerosols can also cause cloud formation and red, orange, beautiful sunrises and sunsets. So like we see here in this image, we could see the satellite image shows two examples of aerosols. First, a large dust storm is blowing across northeastern China towards the Korean peninsula. And you could see the direction. It's coming from the west towards the Korean peninsula and the dust storm through the satellite imagery. And then we could see that dust can provide beautiful sunsets. So dust in the air can cause sunsets to be especially colorful. And ozone is another important gas. Ozone is the components of ozone. It's a molecule of oxygen containing 3 oxygen atoms. And ozone is found in the stratosphere layer known as the ozone layer. So here in this diagram, we have the layers of Earth in a simplified diagram form, but just to introduce it here on this slide, we have the troposphere as our first layer, the stratosphere as our second layer, and then the mesosphere as our third layer. And within the stratosphere layer, we have the ozone layer. So this is where you could find the highest concentration of ozone. and this is found at higher altitudes from 10 to 50 kilometers. I like to call the ozone gas as our primary sunscreen, as our first defensive sunscreen because it absorbs harmful UV radiation. And how do we get ozone? Well, basically, in this altitude range, oxygen molecules, which consist of two atoms of oxygen, are split into single atoms of oxygen when they absorb UV radiation emitted by the sun. Ozone is then created when a single atom of oxygen and a molecule of oxygen collide, forming ozone. And another important issue I'd like to talk about is the Antarctic ozone hole. So here we could see in this satellite imagery on September 28, 2016, the ozone hole extended across an area nearly 3 times the size of continental United States. So here we could see ozone loss at the bottom of the South Pole, the Antarctic zone, the Antarctic area. How did this happen? Well, this is due to CFCs, also known as chlorofluorocarbons. And chlorofluorocarbons are chemical compounds made up of atoms such as carbon, chlorine, and fluorine. And when CFCs are released into our atmosphere, they break down ozone in the upper atmosphere, which is the stratosphere layer. And CFCs are common in refrigerants and aerosol products. So again, manufactured chemicals break up the ozone molecules in the stratosphere, weakening our shield against UV rays. Measurements over the past 3 decades confirm that ozone depletion is occurring worldwide and is especially pronounced above Earth's poles, like we see here over the South Pole. So who created CFCs? Well, the inventor is Thomas Midgley, and he created CFCs to help the problem of refrigerators exploding. So he thought CFCs would be a safer alternative for refrigerators in that time. So he created it in 1930. And when he did create it, it was sold under the brand name Freon 12. So that was the world's first CFC. Even though now today CFCs like Freon 12 are banned or severely restricted due to the Montreal Protocol in 1987, they still linger in the atmosphere. So according to NOAA, CFCs have an atmospheric lifespan of up to 140 years. The Montreal Protocol is considered a success because it has led to the phase out of ozone depleting substances like CFCs and put the ozone layer on a path to full recovery, even helping to mitigate global warming. So as a global issue, this is being resolved. Again, there are harmful effects when you are depleting the ozone layer. It causes more UV radiation to reach the surface, and UV radiation is known to cause cancer. It impacts the human immune system, and UV radiation can also promote cataracts. So definitely be sure you're wearing your sunscreen to help protect you from the harmful UV radiation. Now let's look at the vertical structure of the atmosphere, and let's first take a look at, at this graph here. Okay, making sure I have my pen here. So on the x-axis we have the pressure represented in millibars, and at the surface we can see there is a higher pressure at 1,000 millibars. And then we could see on the x-axis pressure is decreasing all the way to 200, for example. And then here we have the altitude, which is the y-axis. And so we can see that as we go higher in altitude, that pressure decreases. And here it gives an example of the air pressure at the top of Mount Everest, and that is between 300. So it says here the air pressure at the top of Mount Everest is at 314 millibars. And then if you're going up, and this is a weather balloon, I believe, and the air pressure at this altitude is 9.6 millibars. And now we could see a side profile of the gas molecules. So here, when you're at a higher altitude, we see fewer gas molecules, which represents lower pressure compared to at the surface, which has a high concentration of gas molecules. And the average sea level pressure is 1013 millibars. So atmospheric pressure, the definition, it is simply the weight of the air above, so the concentration of gas molecules above that certain point, and pressure is measured as a millibar. So like we saw with the pressure, an increased altitude means that there will be a decrease in pressure. And also, as we go higher in altitude, in our first layer, the troposphere layer, we see a decreased temperature in the troposphere. And we see this visually too when we see the mountains nearby where we live. We see that the snow-capped mountains, and that's representing the decrease in temperature. So snow-capped mountains and snow-free lowlands are a reminder that temperatures decrease as we go higher in the troposphere. But not every layer in the atmosphere, the temperature decreases. Again, here we could see the temperature on the x-axis. Here we're looking at Fahrenheit and Celsius. So I'm used to the Fahrenheit. So let's look at the Fahrenheit scale. And we could see 0 degrees, and then warmer temperatures, and then cooler temperatures are this way. So we could see, and then this is the height, the altitude of our atmosphere and where we find these layers. So like I just mentioned in the previous diagram of Earth's atmospheric layers, we have the troposphere, the stratosphere, the mesosphere, and the thermosphere. And this is the order of the layers from at the surface to higher up in altitude. And we can see here that what separates these layers are, for example, the troposphere is separated, or the top of the troposphere layer, it is called the tropopause. So that is the boundary layer separating it from the stratosphere. So in our first layer, from 0 to 10 kilometers, we could see temperature is decreasing. And straight at the top of the troposphere, the tropopause, we could see the temperature is negative 80 degrees Fahrenheit. So it dropped consistently. So now for our stratosphere layer, found between 50 kilometers to 10 kilometers roughly, we have our stratosphere layer, and we could see that the temperature is warming as we go higher in altitude, and this is due to the ozone gas, the ozone layer. The ozone layer is found in the stratosphere, and that's because the ozone gas absorbs the harmful UV radiation. And then with our third layer, we have the mesosphere, and temperature is decreasing, and we could see at the mesopause it is negative 120 degrees. And then in the thermosphere, the temperature is increasing. So this is the temperature profile of our 4 atmospheric layers. And this is giving us a rough overview. The troposphere temperature decreases with altitude, and the tropopause marks the top and the lowest temperature for the troposphere. and the temperature increases with altitude in the stratosphere. And in this graph, it's showing us the temperature profile of the troposphere layer and where we find the height of the tropopause. So if we look at this graph here, we could see that the height of the tropopause at the equator, it is higher compared to the poles. And we see that here as well. So this is the height of the tropopause. The altitude of the tropopause is 17 kilometers, for example. So 17 kilometers here compared to the poles, which is around 8 kilometers roughly. And the reason for that is because we have along the equator warm air rising. So as warm air is rising, known as the equatorial low pressure, it is pushing up the boundary layer of the troposphere. So that is why the tropopause is higher, has a higher altitude compared to the poles where air is sinking at the poles. Again, with the mesosphere, temperature decreases with altitude. The mesopause marks the top and its lowest temperature, so it's the boundary line. And then the thermosphere has no well-defined upper limit. The temperature rises due to oxygen and nitrogen atoms absorbing very shortwave, high energy solar radiation. So that is the reason why temperature increases at the highest layer. And the ionosphere, this is an electrically charged layer, and this is located 80 to 400 kilometers above the Earth's surface. At this altitude, atoms of oxygen and nitrogen become ionized and absorb shortwave solar energy. And this is where we could find beautiful displays known as the auroras. And auroras are a bright and ever-changing display of light caused by solar radiation, like we could see here in this image. And auroras have different names depending on the hemisphere, so aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. And the Earth's magnetic fields traps these solar particles to show these beautiful displays. And auroras emit light, and auroras usually occur between 60 and 75 degrees of latitude, which covers northern parts of Canada, Norway, Sweden, Finland, Alaska, and Russia, as well as all of Iceland. And the aurora borealis are potentially visible under dark skies from late August to mid-April, preferably under a clear, cloudless sky. I have not seen the auroras before, but that is on my bucket list for sure. And that is it for our lecture today. Feel free to use these links that I have provided here on the YouTube slides so you can get additional information on these topics. And again, for your classwork this week, your assignments this week, you just need to answer the discussion questions. So make sure you do your initial discussion post by Thursday midnight and respond to your 2 classmates' responses by Friday. And also, your quiz is on chapter 1, which is based on lecture as well as the chapter 1 readings for this week. And for next week, we will cover chapter 2. So thank you for listening.